Learning Outcome 2, Functions and Graphs. 12.1.2. Demonstrate an understanding of the definition of a logarithm and any laws needed to solve real-life problems. Do you remember what we covered the last time we met, Deboho?
Didn't we revise exponents?
That's right. And today, I want us to look at the inverse function of exponents, or what we call logarithms. By the end of this lesson, you should be able to simplify expressions containing logs, solve equations using logs, in the same way as multiplication is related to division, or addition is related to subtraction, exponentials are related to logarithms.
Didn't you say earlier that logs are the inverse function of exponents? Is that what you mean by a relationship between logs and exponents?
Yes, that's right, Debo.
All right, but I'm not sure what you mean when you say inverse function.
Let me explain. When we talk about the inverse function, what we mean is that the answer becomes the question and the question becomes the answer. In other words, if we defined an exponential function as a to the power n equal to x, this could be seen as a question and an answer. The question being, what is a to the power n equal to? The answer would be x. The inverse function would be log base a of x equal to n. This is also a question and an answer. The question being, to what power must we raise a in order to obtain x? The answer would be n.
I think I understand what you're saying. So if x squared equal to 9 is the exponential form, then the log form would be, to what power must x squared be raised to give me an answer of 9? And the answer would be 2.
Very good, Deboho.
Does this mean then that we convert between logs and exponentials?
That's right. And we can use this to find the value of either a log or an exponent. This is useful when we have equations that we want to solve that have the unknown in the power. In that case, we would use logs to work it out. For instance, if I wanted to find the value of log base 7 of 343, if I convert this to an exponential equation, my question becomes, to what power must I raise 7 to get 343?
I can work that out. We covered this when we did exponential equations. All I need to do is use my calculator. 7 to the power 3 is equal to 343. So that must mean that log base 7 to 343 is equal to 3.
I think you've got it, Debo. If you want to, you can try this for yourself. Apply the definition in order to calculate the value of the log in each of the following.
Can I ask a question?
Yes, of course.
Does it matter what the base number of the log is? I mean, is log base 2 of 2 the same as log base 10 of 2?
No, it isn't. Much like 3 squared isn't the same as 5 squared. Each of these logs is asking a different question. In the first case, it is asking 2 raised to what power equals 2? While in the second case, it is asking 10 raised to what power gives 2? So you can see they are asking different things. Generally, when we work with logs, we use a common base 10 or a natural base e.
E, what does the e stand for?
E is what we call a natural base. It's a bit like pi. It's an irrational number equal to approximately 2,71828183. A natural log or a log with a base e is commonly used in the sciences, as is a log with base 10. Because these bases are so often used, we've developed shorthand for them. For example, Log base 10 of x could also be written as log of x. So, if you see a log written without a base, it means that it has a base of 10. Now, just like there were laws for exponents, there are laws for logs. These laws are similar to exponential laws, and you will need to learn them. The first log law says that log of 1 is always equal to 0. And this makes sense as anything to the power 0 is equal to 1. The second law is that if the base and the number of a log are the same, the log is equal to 1. If we convert this log into exponential form, we see that this is true according to the laws of exponents. The third log law states that if you multiply the numbers, you can split the log into two separate logs and add them together. The fourth law, if you divide the numbers, you can subtract the logs. Law 5 says that if the number is raised to a power, you can move the power to the front of the log and multiply. And lastly, Law 6, which says that if you take the root of a number, you can divide the log by the root.
Wow, that's a lot to remember.
I know it seems like a lot, but once you start using the laws regularly, you'll start to remember them easier. But for now though, I want us to look at an example for each of the laws. We'll start with the first law and work our way through each of them. Using this law, do you think you can simplify this expression?
Yes, I think so. The law says that log of 1 is equal to 0. So this is 0. And 0 plus 5 is 5.
Good. Now let's try the second law. Using this law, simplify the expression for me.
Easy enough. Log base 10 of 10 is equal to 1. 1 times 100 is 100.
Nicely done. Now let's try an example that uses law 3.
That simplifies to log base 16 of x plus log base 16 of y. Hey, this isn't as hard as I thought it would be.
No, it isn't. Let's look at the next law. The law says that if we divide the numbers, we can subtract the logs.
All right. That means that this must simplify to log base 8 of 100 minus log base 8 of 8. And this can be simplified even further using law 2. Log 8 of 8 is then equal to 1. So we get log 8 of 100 minus 1.
Good, Deborah. Law 5 says that if the number is raised to a power, you can move the power to the front of the log and multiply.
So I move the 10 to the front and multiply by the log.
Now, the last law. Apply this law in this expression.
If I apply the law, I get log base 2 of 5 all divided by 3.
Not bad, Deborah. And now that you're a bit more familiar with the laws, I think you're ready to move on to a more complex example. In this example, we need to simplify the expression without a calculator.
So where do we start?
The first step, whenever we simplify logs, is to see if we can write any of the numbers as exponents with prime bases. In this example, the first log already has a number with a prime base of 2. This second log, though, has the number 125, which isn't prime. We can, however, rewrite it as 5 to the power 3. Next, we need to check that the logs have like bases, which in this case they do. Even though it isn't written, both logs have a base 10. Now we can start to apply whatever laws are necessary to simplify the expression. This second log here has a number raised to a power. So we move the power to the front of the log and multiply according to the fifth log law. I want you to notice something important here. You can't apply the law that says if we add the logs, we multiply the numbers just yet, because we have numbers in front of the logs. But we could, however, take out a common factor of 3, which would leave us with log 2 plus log 5 inside the bracket. Now we can apply the addition law, which gives us log 10 in the bracket. We also know that if the base and the number are the same, the log is equal to 1, according to the second law. The base here is 10, and the number is 10. so it gives us 1. And finally, 1 times 3 is 3, so the answer is 3.
It's amazing that all this simplifies to just 3. Do all log expressions simplify to answers like this?
Unfortunately not. Sometimes, like in this example, they do work out perfectly, but there is no guarantee.
Can we try another one?
Okay, here's another example for us to try. Do you want to try it on your own?
Okay. First I need to write any numbers I can as exponents with prime bases. So 8 is 2 cubed and 32 is 2 to the power of 5. This first number here is an exponent and not a log, but I can still simplify it. I'm raising a power to a power, so I multiply the powers. 3 times 2 over 3 gives me 2, which means that the base is squared. 2 squared is equal to 4. For the log, I can apply the law that says that if you have a number raised to a power, you move the power to the front and multiply, which gives me 5 times log base 2 of 2. Now the base and the number in the log are both 2, so the log is equal to 1. That gives me 4 plus 5 times 1, which is equal to 9.
Well done, Debuho. I would like us to now look at a formula which sometimes makes working with logs easier. It's called changing the base. If we are given log base a of x, we can change this to log base b of x divided by log base b of a.
Can you show me that using numbers?
Good idea. If we had log base 2 of 12, for instance, we could change the base by writing it as log base 10 of 12 divided by log base 10 of 2.
That's easy enough, but do we have to use base 10 or can we use any base?
You can use any base that's convenient for your calculation. I've chosen base 10 because it is the base we use most often and it makes it easier for us to work out the value on a calculator.
That makes sense. Can I try one?
All right. If I give you log base 2 of 4, can you change it so that the base is 8?
Okay. The number goes to the top and the original base goes to the bottom. So that gives me log base 8 of 4 divided by log base 8 of 2.
Good, Debuho. Here's an example for you to try on your own. Okay, now that you know how to simplify expressions, we can move on to the next section, solving equations using logs. In grade 10, when you covered exponential equations, you could only solve some equations by trial and error because you hadn't learned about logs. Now that we know more about logs, we can use them to help us solve those type of equations easily. This equation, for example, you would previously have struggled to solve. I'm going to show you how easy solving this type of equation becomes once we use logs. When we have an equation where the unknown is in the power and we can't make the bases the same, as is the case here, all we need to do to solve the equation is log both sides and then simplify. We know from our log laws that if the number is raised to a power, we need to move the power to the front of the log and multiply. Now, in order to get x on its own, we divide both sides by log 7. Then using a calculator, we divide log 5 by log 7, and we get that x equals 0.77 rounded off to 2 decimal places. It's important to note here that if you're going to solve for x using logs, you first need to try and find a single term on each side of the equal sign. If there are more terms, it makes logging a great deal more difficult.
Wow, that's really easy. Can I try one?
Yes, but this last example was very easy. Before I let you do one on your own, I'd like us to try an example that's a bit more complicated. In this example, as in all exponential equations of this type, we must remember to first simplify as far as possible before we can log both sides. In other words, we need to get a single base with only the unknown in the power on its own on one side of the equation. On the left-hand side over here, we can see that we are adding the powers of the base 2. The rule says that if we add the powers, we must multiply the bases. So we can split this into 2 to the power x times 2 to the power 2. And in order to get the 2 on its own, we divide both sides by 2 squared. Now that we've done that, we can log both sides. Why don't you take it from here, Teboho?
Okay. On the left-hand side, I can move the x to the front of the log and multiply. On the right-hand side, I can simplify 1 divided by 2 squared by bringing the denominator to the top of the fraction and making the power negative. This means that the number of the log now has a power, so I can put this power in front of the equation and multiply. Now to get x on its own, I can divide both sides by log 2. I don't even need a calculator for this because log 2 divided by log 2 must be 1, which means that x is equal to negative 2.
Excellent work, Teboho. Do you think you can handle these on your own now?
Yes, I think I can.
All right, let me give you some practice examples for you to try at home because it looks like it's getting late and I don't want you to miss your lift. Solve for x in the following equation.